All right, good morning,
Oh,
everyone.
really?
Welcome to the second part of Doron's lectures. Hopefully, even if we forgot everything from last week, we can still follow. Okay.
Okay, thanks. So, right, so this is the second part. I will do a recap of what we did last time. So first of all, I already wrote on the board the very basic recap of presentation theory of finite groups. So let me remind you that representation of a finite group or a compact group is just a group homomorphism from the group to matrix groups over the complex numbers. And we think of representations as equivalent if it's the same homomorphism up to a change of basis of the matrices. And we can, whenever we have two representations, we can look at the direct sum of them. And then we just get, we sum the dimension, we get this matrix, the block matrix. And we say that whenever we can write, whenever a representation is equivalent to such a sum, it is called reducible, and otherwise it's called irreducible or irreducible representation for short. And the adjacency matrix. So another example, important representation of any group, any finite group, is the regular representation, which is, you can think of it as the adjacency matrix of the Cayley graph with respect to, if you have one generator, I mean, the regular representation is exactly the adjacency matrix of the Cayley graph. And the regular representation, this is a basic fact in representation theory, when it is reducible, and if you decompose it, you get all the irreducible representations of the group, all the up to equivalence. And each one of them appears with multiplicity that is equal to the dimension. So for example, in the symmetric group on 3 elements, sorry, I'm using the notation same. In the symmetric group on 3 elements, so the regular representation, like the adjacency matrix of the Cayley graph, is 6 by 6. And the composition to reducible looks like that. So we have 3 representations for the symmetric group. They are denoted, they can be named by Young diagrams with 3 boxes. This is the trivial one. This is the sign. And this is some 2-dimensional one. So this trivial representation appears once, the sign appears once, and this one is 2-dimensional, so it appears twice. Okay. Any questions? Okay, so I'll start with so my plan today is I have 7 parts. I think I will probably not I won't get to all of the parts, but I mean, actually the last one, the 5th and the 7th one are the nicest ones. So I don't know, I'll try to skip some details on the way.
Continue this evening over beer.
Yeah, exactly. And I want to start with a recap on SN and remind you what is the Aldous conjecture only in the framework of the representation theory. And I'm not going to give all the 3 of them like last time. And then say the conjecture, the exact conjecture in the unitary group, and then start going over what we know. So first is a recap on. Okay, so first of all, what is the Aldous phenomenon in general? So, okay, I'll write it like that. So I hope I'm going to explain slightly differently from last time. I hope it will be clearer because last time there were some difficulties. So let's assume we have a probability distribution. So the sum of weights is 1. And the weighted Cayley graph G with respect to this distribution. Okay, so I have an weighted edges with respect to each one of the elements of the group. with the corresponding weight has spectrum. So I mean the spectrum of the adjacency matrix. So we have, I mean, it's G by G matrix, so we have G real eigenvalues. Right, I need to assume that, yeah, this should be symmetric. I did, okay. So I also wanted, okay, this guarantees that this means that the Cayley graph is symmetric and then all the eigenvalues are real, not complex. Okay, lambda 1 is always going to be 1 because the sum of weights is 1. And by what we said before, so right, this is just the eigenvalues of the regular representation of the group. If I sum up over all the, let's say, so again, recall that the adjacency matrix of the Cayley graph is just a sum over all the elements of the group. The weight of G times the regular representation of G. And if I change the basis and I look at the equivalence representation or the equivalent way to write the regular representation, I see that every eigenvalue comes from one of these blocks, namely for one of the irreducible representations. The trivial one here, the trivial representation just maps every element to 1. So what I have here is the sum of weights, right? So every eigenvalue corresponds to associated with some era of G. Lambda 1 is 1 associated with the trivial one. So this is a trivial representation, and the question is which irrep does lambda 2 come from? Okay, so this is basically the Aldous question, and Aldous-type phenomenon, or Aldous phenomena, for G, for group G, means that there is a family of probability distributions W and some irrep or not, such that lambda 2 comes always from, such that lambda 2 comes from this or not for every W in the family.
So it's the Aldous phenomenon for a family.
Yes.
What does it mean exist?
Aldous phenomenon for G means that there is a family of, okay, I mean,
Interesting family.
interesting family.
I mean, for S, for the symmetric.
Yeah.
What was the family?
So let's recall. So for the symmetric group, so but before that, I want to say it in a slightly in an equivalent way. So instead of looking at the Cayley graph and thinking about lambda 2, what I can say is that I look at all the irreducible representations except for the trivial one, and I wanted this representation will dominate all the other ones. Okay, so equivalently, then I will then say what happens. I will remind you what happens with the symmetrical. So equivalently will denote by lambda max so this will be the largest eigenvalue of what I get in the representation row under the for W. So let us write it. So what do I get? The large eigenvalue of what? So what we have here in the corresponding block of the regular representation, what we have is exactly the sum over G, the coefficient of G, times rho of G. Okay, so this is just a matrix. This is the average value of this representation with this distribution over the element of G. And on another way to write it is just the expected value when G is distributed according to W of rho of G. Okay, so
It's the largest operator norm of any block.
this is just the operator norm of this block.
And this block.
If rho is irreducible, this is just one block. This is the operator norm of this. It's not really I mean, here it's just a positive grid. It's not operator norms actually. I mean, just the largest positive eigenvalue. You could have negative eigenvalues, which are larger in absolute value.
Oh, okay, you don't care.
Yeah, I mean, I could care, but this is not what.
Good, fine.
Yeah. So just really the largest. I mean, these are all symmetric. Everything is symmetric. All the matrices are. You can think about them as symmetric or at least Hermitian because of this condition. And so, okay, this is just the definition equivalently. So the Aldous phenomenon. Is equivalent to say that for every irrep rho, which is not a trivial, we have that lambda max of rho with respect to W is smaller or equal than lambda max of rho naught with respect to W. Okay, so the largest eigenvalue of rho naught is larger than the largest eigenvalue of every other non-trivial representation.
I guess my objection was that, you can have some trivial family like.
Yeah, but that's
So
not.
it's interesting only
Yeah, I mean, okay, yeah.
with respect to a family.
Yeah, but for example, so, okay, let me say okay, so the first instance where this all started was this paper I mentioned last time of the coincidence Shashahani from 81, where they proved this in a symmetric group, where this is, and it's only for the complete, for the uniform distribution on transposition.
Yeah.
Uniform, only one,
One,
but it's still for, even that, it was for every n, so there is something, I mean, it's not just something you can check in the computer, because you have infinitely many symmetric groups, and it was true in each one of them, so even this was interesting, okay? So it could be a very small field and it's still interesting. And
So if I can get the space of all probability distributions, for each point, it's about just some unit ball inside some high dimension space. For each point, I get some representation. Do you know how
Yes.
this map behaves? Is that
no, this is a very hard question in general. So
for instance, what's the typical, like, what's the measure for any representation? You get some measure of
Okay.
any.
I mean, this is a good question. I mean, I can say something about symmetric group, but it's a hard question. I mean, I think basically, I mean, you should expect that representation of small dimension will be more popular as a dominant because there's basically, I mean, you could think about it because of this multiplicity. So if you have a large dimensional representation with a large eigenvalue, I mean, this representation appears in large multiplicity. It means that there is a large eigenvalue with large multiplicity, and this is like not. I mean, somehow you expect at least in a random graph, even if it's a random Cayley graph, that the eigenvalues will converge to something that has some concentration near zero and not. I mean, there is something. There is a way to make it like an actually mathematical statement. There is some principle that Sarnak and Shu where they show this kind of this phenomenon, but it's not precise, not precise words.
They use multiplicity to prove expansion.
Yes,
The multiplicity of eigenvalues in groups where you have only large dimensional representation. You can use this.
Upper bound, second largest eigenvalue.
Yeah, you can list up. This was the beginning of all the later sequence.
The gauss.
Bourgain, Gamble. This is the original idea with the multiplicity is essential in this.
Okay, so again, so Aldous in the symmetrical. So okay, so first of all, let me remind you that EREPs of the symmetrical and here we just think of it as names. These are they correspond to Young diagrams. With n squared. So this is yeah, so this represents this is a name for representation of S symmetric over 7 elements. And I will so unlike last time, I want to denote by the standard representation of the symmetrical. I want to think of it as the n-dimensional representation, which maps every element to a permutation matrix, every permutation to a permutation matrix, and this one is reducible, and it decomposes to this one plus the trivial one. This is trivial. This is n-1 dimensional. Okay, and now the Aldous, so Aldous conjecture. Which was proven by Caputo, Liggett and Richthammer in 2010, says that so you have Aldous phenomenon with W is any distribution on distribution. And one not is this one, this n-1 dimensional representation. Okay, so again, it means that if you take any distribution on transpositions, you see that the largest eigenvalue of this representation is larger than the largest eigenvalue of any other non-trivial.
Right, and you told us it's conjecture to be true for any distribution.
Right. Yeah.
Do you know if it's true for like 3 uniform?
Uniformity is true.
I mean, fix some 3 uniform.
Uniform, you mean?
Take uniform distribution on the symmetric on 3 elements.
So uniform, you mean same weight for all the sets in this with this. Okay, let me first. I plan to write it. So Caputo conjecture. So this is a conjecture of Caputo. Then, so I'll call it Aldous for hypergraphs. So with still with the same representation. Okay, so what does it mean? So we give so I mean hypergraph just means we think of subsets of 1 to n. So we have any probability, we fix any probability distribution. We call it W naught on the sets, on the subsets of of 1 to n. And then we take, so we choose. So now I'm telling you what W is. What is the probability distribution on the entire group? So we choose E. According to this probability solution W naught, and then choose uniformly at random sigma some permutation in the symmetric group on E. So this means that I look at all permutations that where the support is contained in this subset. Okay, if all the subsets here are of size 2, then we recover this case of transpositions. Because I mean, as I said last time, I mean, the difference between transpositions and the entire copy of S2 is just adding laziness to the work. So it's really equivalent. And now you're asking about, you're asking about 3 uniform. So you mean that W. So you want this to be, I mean, this is known in several cases that are not included here.
Yeah. And I was asking if for the case that the hypergraph is arbitrary 3 uniform.
No, so this is not known. Not known for arbitrary 3 uniform.
And I assume you believe it is false.
False?
Yeah.
No. What, the conjecture?
Is it general? You believe it?
Yeah, sure it's true.
Really?
I'm sure it's true.
Yeah.
Who else is true?
I don't know. I was also
Ah,
excited.
I doubt it very much, but that's my feeling.
No, sure it's true. I mean, it's still, I mean, it's not like if I just take, for example, all the 3 cycles with any probability solution, this is false. I mean, we know it's false, even though it seems like it's still, there is something that happens after when n is large enough, even for only 3 cycles, but yeah. Here we take, when we take a 3 cycle, we also take all the transpositions inside, and yeah, no, I'm.
It always has a support on like a somewhat big support on transpositions, right? Like you never forget the fact that you sample transpositions with some concept.
Yeah, but
Yeah.
So what?
No, I don't know. I'm just saying that like.
No, I mean, this stood a lot of tests. So we have, there are many simulations that support it and many partial cases that support it, so.
No, but simulations maybe choose the hypergraph
Yeah, you're right,
not
like,
adversarially, so.
yeah, you're right, but. Yeah, I like a physicist who thinks that. That we don't need.
How do you have intuition about this at all?
It just sounds so strong, but I don't have much.
I would say, how would you think about it? If your hypergraph is 3 uniform, and you look at the skeleton, which is a 2 unit, it's a graph, it could be that the skeleton looks like, one thing, and the transpositions will actually show that. But then, like, the 3 uniform edges might actually have a bottleneck somewhere that's, so the transpositions kind of show as if you're expanding, but
It doesn't even talk about expansion, maybe it's not.
it's talking about lambda too, so.
Yeah, usually, I mean, these are very, I mean, this is very far from being sparse, right? I mean.
No, I can construct the hypergraph sparsely, for example.
Yeah, but
Like
still, I mean, but then
All the
you,
symmetry is inside.
yeah, but you have all the symmetry.
The symmetries
Then
are
it will not generate.
in each hyper.
It has to generate.
No, what do you mean? You can take like a string of triangles.
Yeah.
It will generate.
No, I agree. This will generate.
Yeah.
Anyway, I think that there's so much room for the lambda 2 to appear, and you shrink it to this tiny corner in all.
Yeah, that's the,
That's my,
Making it
the only
work.
intuition I think.
Yeah.
Is there any abelian counterpart of this? So
No, there is no ordering by dimension. All of them are one, all
Yeah.
representations are
the
one.
dimension wise, it is true.
So how would you prefer one curve?
Yeah,
to
right.
another?
For example, in the hypercube, there is you for characters you can assign degrees, right? There is an ordering of
It's arbitrary, it's basis dependent.
I mean, we have some cases here where we have 2 representations of the same dimension. Even here, right, we have the transpose of this, like this times tensor with the sign is the same dimension and
Very different actually.
Yeah, and it's still, there is a clear order. By the way, I think for this, what you said with triangles, it's true. I mean, there are some hypergraphs which are very sparse. If you have, for example, an hyper edge that covered, sorry, a vertex which is covered by a unique hyper edge, you can use, there's an induction step where you can get to a smaller graph. So it might even be true in the case that you mentioned. I mean, true, proven. Yeah. Okay. Okay, so this is SN. Any other questions?
You promised to show us some parts of this CLR, right?
Yeah, this is part 7.
Okay.
Okay, no, but I mean, okay, I can skip other stuff and sorry, this is really nice. The sketch of the proof is really very elegant, so. So, okay, Aldous phenomenon. Okay, so last time I tried to take you through the journey we had. Now I'm just going to get to the bottom line, which is the conjecture. So there is a way, I'll just mention it, there is a way to think about something that is analogous to the Cayley graph, but it's much easier to think about it like this. So I want to find probability distributions on unitary groups and to find a non-trivial irreducible representation which dominates all other ones like here above. And we're going to choose the probability distribution exactly in this framework in the Caputo, like the Caputo conjecture. So again, W is the same. So what probability distribution I want, I'm taking again a hypergraph distribution as before. So it means I have a hypergraph with weights, and you can assume, I mean, I want it to be a probability distribution. It's not important, but it's easier to think about it like that. So I have a weight on every hyper edge, and the sum of weights is 1. And what I do is I first choose my hyper edge according to these weights, to this probability distribution W naught. And then I choose uniformly. So I just need to change this. So I choose, instead of a uniform permutation, I use a uniform unitary matrix. Okay, so I choose A. So I will write it like that. U of E, uniformly at random. And here uniformly means R. So R is a natural probability distribution that you have on every compact group. And I will say more about it later. And UE, just to be on the safe side, so for example, if E is the set 1, 2, let's say 1, 2, 3, UE is, first of all, it's like U3, and this is the matrices like that. Okay, so I use this embedding in the coordinates 1, 2, and 3 of U3 inside UN. Okay, and the conjecture. Oh, sorry for that. Okay, before I state the conjecture, I'll remind you that irreps of UN, and again, you can think of them as these only as names. These are so for every irreducible representation of UN, there's a name which is given by n integers, which are non-decreasing. There are infinitely many of them for every n. And I will think of it, so today, I think it will be helpful to think of them like similarly to Young diagrams. I want to think of to draw things that look like that. Okay, what is that? So this is, I think of it as like I have a Young diagram and a negative Young diagram. This corresponds to 3, 2, 1, 1, 0, 0, minus 1, minus 2. Okay, I think it will be easier to draw this diagram than to write this sequence of numbers. Okay, which is just a way to think about these sequences. And like my remind you, so the standard so the trivial representation, this is just this line, so it's zeros. And it takes every element just one. Every matrix takes to the 1x1 matrix with 1 inside, 1-dimensional, and the standard, which is this one. Okay, so this is 1, 0, 0, 0, 0, and so on. This just takes A to A. Okay, this is an n-dimensional representation. Okay, and as before, so I'm going to write it again. Lambda max of rho and W is the same as just largest eigenvalue. So exactly as before, I just want to stress that nothing changed. I write it like that, the expected value. I take A according to W. Okay, so I pick A at random according to this probability distribution, and I evaluate the representation at A. So this is just a matrix, and look at the largest eigenvalue. So this is exactly what we had in the systematic group. It's the same. And our conjecture, by the way, Gil is not related to Nogal in any way. They know each other, but they're not related. So for every hypergraph and W, so I mean any probability distribution that is given by a hypergraph as before. This one or this one rules. Okay. So it's not okay. It's not exactly like what I said before. Like we had one irreducible, now we have two, and we know that we need at least these two. I mean, we have cases where each one of them is needed, but we think either one is always true for any hypergraph. Okay, so should I write explicitly what this means?
Can you just say, is that 1, 0 or?
Yeah, this is like 1, 0, 0, 0, 0, minus 1.
Can you
And this-
remind us what that is? Like, it's A conjugate, right?
Yeah, so I'll say it. Yeah, I will say it in a second.
Okay.
But yeah, so this is irreducible representation. I mean, I mean, to be fair, also here in the symmetric group, I mean, if I give you a Young diagram, it's not that easy to understand what this representation is. But here it's the same, but I will.
Are you gonna remind us why you can't just, I mean, why the baby case of this conjecture is false, or it's not so?
The baby case, this one? Just, I mean,
The way you described the story last time is you assume, you tried to check if that's the right
Yeah.
answer and you found the counter or something.
right. So basically, yeah, what I said is we for a long time we thought this was the only reason, the only thing we needed, but we were too random. Our simulations were too random. We took random weights, but then when we took all the weights to be the same, we just computed. We saw that this one rules. Yeah, this one is the large eigenvalue here was larger than here.
Do you understand, like, is there an explanation for that?
So for what for why yeah, I don't have intuition why here we need more than the symmetrical. I mean, why? No, I don't have a good intuition for that. But I mean, but we know. I mean, it's not like we did we created some simulation. We thought it was that, and then we find a couple of examples, so we enlarge it. I don't think it will, and then we find that. I mean, now we have some like real cases where we know this is true. So I mean, it's not like we think we didn't miss anything else. Yeah. So just again, perhaps I don't want to write it. I'll just say again what it means. That if we take the maximum eigenvalue of this representation with respect to W, and the largest one of this one, and now we take the maximum of these two, this is going to be larger than the maximum eigenvalue of any other non-trivial representation. This is what rules means. Okay. Yeah.
Is there any related conjecture for special unitary or orthogonal unitaries?
So okay, we thought about it at some point. I think special unitary is probably, I think it's equivalent. I think we can deduce it from this. So it should be this. I mean, right. I mean, for special unitary, I mean, these are still representation. Usually, they are. I think.
Like it's equivalent conjecture or it follows from it?
I don't remember. I think it follows from this. I'm not sure if it's. I don't remember.
What about orthogonal matrices?
So for orthogonal matrices, I'm sure. Okay, I'm sure there is such a conjecture.
Okay.
I don't know what the answer is, and the same for like matrix groups or finite fields. I'm pretty sure there is such a conjecture. I don't know what, and there is a guess what it could be, but we didn't even carry simulation for this. I mean, it's not always easy to simulate all these representations and so on. So it's not that.
So here there is no restriction on the uniformity of the edges in the hypergraph.
Right. Yeah. Any hypergraph, it should be. I mean, conjectural. I will state. So we know some cases. I will say what we know, but I can say now, and we know it for. So we know it in the first of all, we know it in the symmetric case where all the edges of the same size have the same weight, and we know it in the case where the W naught, this hypergraph, is supported on n-1 on hyperedges of size n-1. Okay, so you have only the nearly maximal edges.
And you don't know it for sure.
We don't know it for pairs. So we don't even know the analog of Aldous, the original Aldous, yeah.
And you use the discrete maybe that you know exactly when either one will appear.
Well, in the uniform, the uniform where all the weights, the weight depends only on the size of the hyperedge. This always rules.
Mhm.
And in the other one, we don't have a nice condition, but both could appear. Yeah. Perhaps I need to look it up again.
Doron?
Yeah.
You're saying one of the two rules, you have to like, is it always, do you have examples where like one of them is strictly better than the other and like it goes both ways?
Yes.
Okay.
Yes. What I'm not sure about is whether they are always the largest two.
Sure.
This I don't know if they are the largest two or if one wins and perhaps a third representation can come in between, because in all the cases we know they are really, they don't only rule, but they're also the first to count. Okay. Okay, so now, okay, so next I want to, so how do we start to think about this? So perhaps we'll call it first computations. Right, I will recall what we said last time. This helps in dealing with with all these reducible representations, which it's not always easy to construct exactly an irreducible representation, but each reducible representation is contained, meaning that contained in RKL for some KNL or RKL is the representation that takes a unitary matrix to the tensor power K, tensor with the conjugate tensor power L. And this is, by the way, the dimension is n to the K plus L, right? So each one of them is contained in one of those. And so I want to state again these examples. So R00 is just the trivial. So this is the trivial, remember? R11 is standard. It's this one. R2 naught is, so A goes to A tensor A tensor. The second tensor power, tensor square of A. This decomposes to this one plus this one. And
the RKL don't contain the trivial.
they don't all contain a trivial, and they contain a trivial only if K equals L. So I'll give you an example. Let's look at L11. So this one contains this one.
So there above you meant R10 and R11.
Sorry. Yeah, so this R11 contains this one, which is one of the important one, and this one is the trivial. And again, this one takes A to A tensor A conjugate, and last example is R22, which takes A to A tensor 2 times A bar tensor 2. This is equal to okay, so it also contains this one and twice this one, and so there are multiplicities. You can see, I mean, there are some rules, for example, I know, so RKL contains all the representation it contains, the sum of weights is K minus L. See, the sum of weights in all of these is 0. I mean, it's always balanced. Here the sum is always 2, here the sum is 1. It's like the difference. And in RKL, the positive weights are at most K and the negative weights are at most L. I mean, these are precisely the conditions that tell you which representations are contained in RKL. Okay. So let's do some computations. So let's start to understand the largest eigenvalue of the representations when I have some hypergraph W naught. So first of all, as a warm-up, what is the largest eigenvalue of the trivial? So this is a probability distribution. The trivial just takes no matter what matrix you get, it takes it to 1. So you just get the sum of weights, and the sum of weights is just 1. Okay, what is lambda max of standard? This is standard. So this is the largest n value of the standard representation, which is just A. Okay, so actually just look at this uniform distribution. No, sorry, not uniform. This probability distribution I have on unitary matrices, and I take the expected value. And another way to say it is that this is let's so I want to take the sum over all E all hyperedges. I take the weight of this hyperedge times the expected value of A inside U. Okay, so to understand this, we need to understand that. So for example, if E is 1, 2, we want to understand what is the expected value of A. Basically, the expected value of this matrix, where these 4 elements are random at U2. Okay, so what is it? So we need to understand, I mean, okay, it follows from another principle we'll talk about later, but we want to understand what is the average value of a coordinate in a random unitary matrix. 0. Why 0? Okay, let me.
For reality, but I guess you are not going to go.
Yes, I want to use, I mean,
But there is a simple argument.
yeah, there is a simple argument, but I want to give an argument that will be helpful for, right? Also for, like, okay, then we'll take this, right? And then we'll need to understand what is the expected value of product of 2 entries in a random unitary matrix and so on. And here we'll need product of 2 entries and 2 entries conjugates. Okay, we'll need to understand these kind of expressions. What is the expected value?
You don't want to do it by taking the expectation multiplying by
Yes, yeah, exactly. Yeah.
So you don't need to look at anything, the whole block. Right? If we forget that.
No. I want to. No. I will need
Individual
analysis.
For this calculation.
Not for this one, right? Not for this one. But this is the simplest example. So let's.
I think maybe people never saw it. I mean, just to see that the expectation over any reducible representation that's not trivial of the value of an element of the group is 0.
Yes.
And the way you do this average, then it's the same as this average times a fixed element of the group, which is not 0. So the only way this can happen.
You need to say it a bit more, but.
That's the gist.
Okay, so let's do about this is okay. So computations. What did you say, Joe?
You want to get to part 7.
Yeah. Okay, so computation in Hall measure of UN. So here's a basic fact about Hall measure. Hall is left and right invariant, which means that if I have any measurable function from my group, so I say for UN, and let's say I have a real valued function from UN to R, and any fixed element in the unitary group, if I take the expected value of F of A, so now A is, it's A is random in UN. It's the same as what I would get if I multiply A from the right or from the left by B. So it's the same as the expected value, where again A is in UN, F of AB. Or the same, F of BA. Like multiply my element, I can shift them by multiplication by a fixed element, and I will get the same result. So as an example, what is the expected value of, again, A is a har in UN, and I just want the ij, sorry, the ij coordinate. What is the expected value? So what I'm going to do is to multiply A by this random matrix, this random matrix. Oh, not random. This fixed matrix, unitary matrix, where I put here all the coordinates are 1 except for the ith coordinate, which is lambda at the diagonal. So it's a diagonal matrix with all 1 except for one value where it's at the location I put I, and then I take the ij coordinates. Okay, what does this do to the ij coordinates?
Multiplies it by lambda.
Yeah, it multiplies by lambda. So this just means that it's lambda times the expected value of aij. But lambda, so lambda could be any element. I want this to be a unitary matrix, so lambda could be any element in the unit circle. So I get a quantity which doesn't change when I multiply by an arbitrary element in the unit circle, therefore it must be 0. And why do I give this proof? Because this proof generalizes. So I can do the same with now if I take two of them, so if I take, for example, let's say A12 times A34, the same, again, I can multiply by a diagonal matrix where I only change the first row. And the first row affects only this one. Again, it will, if I do the same trick, I multiply by lambda 1, 1, 1, 1, 1, it will multiply this expectation by lambda, but by the Har property, it doesn't change. So this is again 0.
So essentially, this trick will always work unless L is equal to K. Right, whenever L is not equal to K.
So let's be right. So let's take, okay, first of all.
That's okay,
Yeah.
take a lambda squared in the circle.
Right, here if I do the same, this lambda, so I need to multiply this A by, I multiply, I get a multiplication by lambda here and here, but overall I get a lambda squared coefficient. Again, this is 0, but, okay, but what happens if I now do this? Okay, so.
Yeah.
Now let's do this 0. Before that, I want to, what about this?
You can still handle it because.
I can still handle it, right? If I change the first row and multiply the first row of the matrix by lambda, it only changes this entry, so I still get 0. But if I take this one, by the way, I can also multiply from the left and change the columns. But here, because I have conjugate, if I multiply A by, if I change the first row by lambda, after I take conjugate, it multiplies by lambda inverse. Because the lambda is on the unit circle, the conjugate is the inverse of lambda. So I multiply by lambda and then by lambda inverse, so I did nothing. So this is not always 0. So what is this?
What else can it be?
What else could it be?
What?
Not quite.
No.
No. So here's another. So let's do it in let's say in A2. Okay, so let's say that's A. Okay, so I want to understand what is the expected value of A, of B, this is B times B inverse. right? But let's notice that if I take A times this matrix, what do I get? I get, BD. Okay, so again, this is a kind of a hard, something I can do with how I multiply by a fixed element, so that expected value of BB inverse is the same as AA inverse. So I write it 2 times the expected value of BB is the same as the expected value of AA bar plus BB bar, which is what?
Sorry, what?
Okay,
2.
AA bar plus BB bar, this is exactly the norm of the first row of the matrix. This is a unitary matrix, the norm is 1. So this is 1. So each one of them is 1/2. Okay, so this is actually, and in general, this is in U2, this is in general 1/n. The same kind of argument shows that this is 1/n. But I want to say more generally. So okay, let's put it here. Okay, but these kinds of things will take, I mean, you need to be more sophisticated to handle everything. So I'll say I want to sum up what we got from it. So first of all, the expected value of I1, J1 up to AJT, sorry, IT. JT times A bar. I want that. Okay, let me just try that. More generally, if the indices are not balanced, we get 0. And otherwise, so in for example, like this is the first case that in these cases where all the indices are we have 1, the same number of times we have 1 for the rows in the non-conjugate part and in the conjugate part. So otherwise, there is a technique called Weinberg calculus. So there are precise formulas for each of these cases. This was developed using the Schur-Weyl duality between the representation of UN and symmetrical. And this was, I just mentioned some names. So it started with some physicists, sorry, not physicists, Liggett and 78 and someone else. 80, then Collins. So then you develop this theory, but basically it gives you concrete formulas to compute all these expressions.
So balance mean you look at they have to be together balance or the number of ones in the non-conjugate part.
The number of
ones in the.
Yeah, you basically, I mean, balance means that this trick doesn't work. So it means that the number of you have the non-conjugate part and the conjugate part. The multiset of indices of the rows here is the same as the multiset of indices of the rows here, and the multiset of columns here is the same as the multiset of columns here. This is basically what it means. But basically, there is a way to do it, but that's to compute it exactly for simulations. So this allows us to compute for simulations precisely all these RKL. Okay. Because every element is just we have a big matrix, but in simulations, I mean each entry in RKL of a random matrix, just can be computed precisely using this.
So you have formulae for different.
Yeah, I mean, I can compute it. It doesn't say anything about which one, what is the eigenvalue and so on. I mean,
You have a formula.
and formulas for each entry.
Pendleton calculus gives me a formula for if I have 4 times this minus 4 times that.
Yeah, no, even for just multiplication like that gives you multiplication like that, and then you can expand
For each monomial.
each monomial. You have every monomial in the entries of a random matrix. It gives you a formula, and this allows you to compute precisely for a given hypergraph with precise weights. You can compute in practice, in theory at least, the precise expected value of these representations.
So for example, if I want to focus on the transposition case where you have 2 by 2 unitaries,
Yeah,
then you know what it is. It's like half, 0, 0.
right. So
For every edge.
it depends. I mean, so here, I mean, this is just right. This is just one entry, so this is just 0.
Oh, right.
It will be in the yeah. So perhaps yeah. Perhaps I'll take a few moments before the break. I want to. Yeah, I think it would be better to finish this part before the break. Okay, so if you think about this example, what we get is you see, so for every, I mean, this is now just I'm returning that standard representation. So just the expected value of just the matrices themselves. For every edge, what I see is that I get it's always diagonal, and I get ones exactly where outside the support of the edge. Okay, so I get here 1 exactly in the indices which are different from 1 and 2. So if I sum over, I do the sum, I get that that the expected value of A, the expected W of A, is the diagonal matrix. Here in this entry, I get the sum of all the over all the edges that don't contain 1 with the weight. Here is self-fold. Okay, so the largest eigenvalue is just the largest one of these partial sums of weights. Okay, so I want to say 2 theorems without I will skip the proofs because they just so actually I'll say it so for every hypergraph W naught, we have that and K is not L. So we basically using such computations, we can show that the standard one dominates all the non-balanced representations. So this one, the largest one here, dominates all the representations as long as K is not equal to L, which means equivalently that the sum of weights is not 0. And this is basically this kind of, it actually follows from, it's not much harder than that. I mean, you have to be more careful, but this one is dominated by this irreducible representation always for every W. And this one And this is why I showed it very briefly last time. This one is the same as. So now I go back to the symmetrical. The largest eigenvalue here is the same as the largest eigenvalue of the standard representation of the symmetrical with respect to the same hypergraph. Yeah, so, okay, I will decide over the break if I will say a bit more about that or not. But let's take a break and then, yeah, so I saved most of the nicer proofs for the nicer ideas for the second part, for the second hour. Take 5 minutes.
It's political.
So, oh, Doron was with the free lunch.
You might.
What's the significance of this last equality? Something that's like worrisome?
There's a connection.
There's a connection.
We started the
Yeah.
Which one between what and what?
between the symmetric group and the unitary.
Where's this, this?
Okay,
It says
so,
the
yeah.
second one is the symmetric.
This is symmetrical. Somehow the eigenvalues of this important representation of the symmetrical appear in the spectrum of the unitary group. If I take the same hypergraph,
And you know why, like you have an explanation. why.
we have proof why. I wouldn't say it's it's a calculation. Yeah, I mean you show that.
Sometimes we answered but the intuition about something. And the answer,
I know.
this is standard.
Hmm?
This representation is the standard one.
Yeah, I just want to use a different. I want to say that it starts with n dimensional one.
Yeah.
You wanna say that what?
No,
I want to
no,
use
it is
the
a
word standard for the n dimensional one, even in the symmetrical. So this is not
Front.
quite. This is
A color.
What is this one?
it's like the one, the n minus one dimensional one.
And the standard includes the extra.
Yeah, the extra trivial there. Trivial.
They get confused when the word regular representation and standard representation.
Right. Yeah. So regular is huge. Standard is
Small.
tiny.
So, what do you feel about this theorem? Is it like, I mean, it's,
This one.
yeah, it says, except for the k equals L, you've proven your conjecture.
Yeah, we are.
So is that how you feel about the theorem or you feel that actually all the interesting stuff goes?
Yeah, we had this babushka experience where
Uh,
we managed to narrow down, but still. Yeah, we were very hopeful because we are able. This narrows. It feels like it narrows down a lot because, I mean, this is like an open condition, right? I mean.
It's like a little of one fraction of the.
Yeah, in a sense, yeah.
No, but I mean.
And then, but these are all. I mean, this is the easier part of the. This is not. You need to notice some stuff. This is not hard. This is the easier part of the. Then you're still left with. Yeah, all the balanced representation where the sum of weight is 0 is still.
It's like in the trace method, it's the balanced words that give you all the headache, all the other.
Always, that's always the
Always,
case, yeah.
So here it is.
Yeah, I was just telling this to Rachel, I guess she's gone. But, okay. So, but you did prove the theorem.
Hmm?
Or whenever on every slice of the hypergraph, you have uniform weight.
Yeah.
In particular, you have all the weight on slices of size 2 and 0 everywhere else, which is the original.
Yeah, the concept honey.
Right?
Yes, yeah.
Okay, so that's the theorem.
Yes, yeah.
You know, the Aldous thing when the W concentrates, W naught, one pair, one group, one, and minus one.
So Peter.
You mean,
Better than
it's fun, but,
San Diego,
so not hypergraph.
So at the San Diego visit day, they had people like making the.
No, but you mean just the cycle or?
I wonder who they hired.
Yeah, no, I never thought that, okay.
You know, Peter,
I know it was the dining.
Just
Oh, no, sorry, it wasn't the dining room. It said in-house and someone was making it.
So they hired somebody.
Yeah.
It's a good.
let me break it to you. They don't have a daily guy making this special. At least for the 6 years
I
that
mean,
I
let
was
me
there.
break it to you. They used UCSD.
If you have a tree, like if that was.
That's surprising, but it's not good.
No, you gotta go to the meetings.
We had this
Right.
conversation.
Okay, you can.
It's okay, it's not a.
If you have a.
But it doesn't give you proof.
It is unlikely.
Remove this vertex
Yeah, this.
and get this smaller hyperlapse without this vertex.
Yeah.
In this case, all the way to.
It was a mistake.
Frankly,
So basically.
one of the better tasting restaurants.
It was bad. I hated
It
it.
might have been a different one then.
שאלת עם החצי, גם מפורסמת.
That
בסביבה הנורמה.
or it's after.
I used to watch That's where I could.
Perhaps like, I would
go בתור קבוע.
and I don't want to flame Peter too much.
The answer is that
בתור
the best
קבוע,
food there is
that.
that
Wait, to be clear, we were talking about best tacos in San Diego City, not best tacos.
Yeah, I think.
Yes,
distribution.
well, location wise and.
Guys making the
אולי
trade.
אחד, יש גם
Not your average restaurant.
Wait, but you didn't say average, you said maximum.
בדיוק הטיעון שלך.
No, but that's not.
Would you like,
Mexico, yes.
תשובה בכל הקשר.
Even like.
Look, best tacos in San Diego includes the random guy that you hired to make.
Yeah, I do believe you said best tacos.
Let's not flame Peter too much. That's wildly incorrect. No, I'm kidding.
I think all we're learning here is that those are pre-registered, like.
Yeah, but they're really far.
Not biased.
It's really far away.
That's all it is.
I see, you're saying.
But it is exciting that there's a.
Yeah, no, it was good.
No, it's good.
We put on like the hot.
Yeah, we have.
That's usually good. But if you.
There's like this.
Yeah.
I like the.
That's the.
I really love that. I think that's also just, it's a flavor I like.
I don't like.
Did you tell us that?
For rank, San Diego is.
I would have heard
it is the only bad enchiladas, those are ranked.
I've never had the.
But then, Mexico food, number 2 is the fish tacos. But 3 was.
I love slaughterhouse.
Number 4, dead last. The pork taco. I can say what taco.
Yeah, I like the hardest. I saw it once.
I will say, I think.
Yeah, that's my fault, I like.
It's not perfectly crispy.
Yeah, the mix of sauce.
לא, זה מסוכן.
Like I was uninspired by the fish taco.
See, I think we understood the bias.
Well, no, I mean, maybe the mayonnaise makes it.
That probably does.
Oh, yeah, that makes a
That
huge.
probably makes a huge difference.
Totally mayo on
It will be, yeah,
Yeah, it just.
היה פה, היית צריך לשאול.
now I agree with you, but only from that.
נראה לי
I'm losing-
תמוה
I'm losing-
שהפעם.
Rachel.
No, I
agree with our conclusion.
the fish tacos.
Wait, why are you saying such horrible things about Rachel? What is?
She agreed with our conclusions.
We're in
Is that
different. I also got the.
נראה לך בסדר שאני אעשה ככה וככה,
Where does that rank?
I think it ranks.
Sorry to
with
have
enchiladas
missed it.
over the enchiladas. Have you been to this?
No, I really wanted to go. but
Yeah,
it's
that's
not
I've been
right.
raving about this place for months.
Horrible.
Okay, got it.
Okay, so before we move on to this was the third part, well, 24 left. I want to just say one word about this equality, because I mean, this is going to be what we saw here. So first of all, you see, we narrowed down the problem. We got rid by this theorem. We narrowed down the problem to only the balanced representations, right? We know that we're only left with a representation where the sum of weights is 0. All the other ones, we know they are dominated by even by this one and this one, and in particular by this one. And I just want to say one word about, there was actually another way we know how to narrow things. In each of the balanced representation, we actually get a square root of their blocks inside the representation. So even though it's an irreducible representation, and in general, it is invariant. There are no subblocks. It doesn't decompose into blocks with respect to all the group. If we just look at our particular elements of the coming from the hypergraph, we still have a more a final decomposition. And I want to just tell you what it is for R11. So remember, R11 takes A to, and this is the representation that takes.
So this hypergraph distribution
Oh, wait.
here is subalgebra, very good algebra.
I mean, for finite groups it is, but
I mean, if you have final representation, it must be a subalgebra. If you have more decomposition.
is it? I don't think so. No, SN it's no, I think generates everything. So
No, in the unit. If you say you have a final.
yeah, but what is the group algebra? Yeah, but group algebra is not defined as well as. But yeah, I guess you can probably yes, yeah, probably in the right way to say it. You're right. Yeah. So R11, I remind you, it's the composition of this plus the trivial. This is 1 minus 1. And so if you write it in the so what you see when you write down these, so these are what are the so the indices of this matrix are pairs of elements, what ij, where I and j are both between 1 and n. So if you write it like that, as first you put all these pairs, and then you put all the other pairs. What you get is that you get this block structure, well, here it turns out by these formulas of that we computed, here what you get is the standard, not the standard, but here you get sorry. Okay, you don't have this block structure in general, but you do have this.
You're talking about the expectation of this.
Yeah, the expectation. Yeah. So first of all, the trivial one is this one. So this, if you just put ones here and zeros here, this is the one. The subspace that is spanned by this vector. This is the one-dimensional representation that corresponds to the trivial representation inside.
Sorry, I kind of lost. What is this vector telling
This
us?
is the eigenspace, I think, right? That's what you.
This is the one that, so I told you before that this is the decomposition. I told you the fact that there is a copy of the trivial representation. If you change the
That's
basis,
Vector that's.
this is the, yeah, there is
The
a,
eigenvector of eigenvalue 1.
yeah, value 1.
Change the basis.
If you change if you write it in a different basis, you have one vector which is where each matrix of each unitary matrix acts trivially, doesn't do anything.
Right, or in other words.
Multiplied by 1.
The eigenvector with top eigenvalue is this one?
Yeah, so this is an eigenvector with eigenvalue 1 for every unitary matrix. If you glue in, you take the unitary matrix and you put 8 tensor 8 with this basis, with this order of the indices.
Yeah.
And if you take the expectation expected over UE for some set of A, if you look at the expectation over some hyperedge, then what you get here is, you get again, you get the same kind of phenomena we had before with the diagonal matrix, where you just get one if these indices are not contained in E. And here you get the expected value of here you get the expected value of the standard representation of the symmetrical with respect to the same set. So this is like a computation shows it. So what I'm saying, what the point is that even though this is like an n squared dimensional representation, and this is true for all the balanced ones, there is a small block which we'll call, let's say, the balance block. So there is a balance block inside the balance representation, and it's balanced because the coordinates here are balanced, 1 and 1, and so on. And this is where the interesting part happens, and there is the rest, which is dominated by this. So we can narrow down even further to smaller blocks than these representations suggest.
So this picture is how the expected matrix looks like?
Yes, for any set. For any set, you get this kind of structure, and therefore also for a linear for a combination of sets, you also get this structure because it's just a linear combination of these matrices, and they all respect the same structure, the same block structure. There is a finer decomposition of these matrices to.
But this is only for R11.
No, this is particular. This particular block is this particular thing is for R11, but you get a similar thing for any balanced one, for any balanced representation, for R22 as well, and you can also do it inside the.
In R2, you have the small block which here is n by n, you will have it n squared by n squared.
Yeah.
You have 1, 2, 1,
Right.
2, 1,
Yeah.
3, 1, 3. Yeah.
Yes, or 1, 1, 1, 1. Yeah.
Of course.
Yes, or 1, 3, 3, 1. Yeah, you have all as long as the coordinates are balanced. Yeah. So the point is that in general, in RKK has dimension n to the 2k, and there is a block. The interesting block is only n to the k. So it's of size of dimension square root. Okay. So. One more remark is that this equality, I told you that you can suddenly find part of the spectrum of the symmetrical inside. In fact, you can find the entire spectrum of the symmetrical. If you fix the same hypergraph, you can get all the spectrum of the symmetrical. You can find it in the spectrum of the unitary group with respect to the same hypergraph, which means that in a sense, this conjecture is harder than Caputo. But of course, sometimes harder means it's easier to solve. It's hard. Okay. So,
The general facts about subtle.
no, it's a. No, it's really unique. It's not. We didn't expect it, and we don't have a. It's not really generalized. Okay, so. Okay, I'll tell you. So I want to make this brief. So as I told you, there is a process. So we have this conjecture. We look at these two representations, but it turns out that there is a way to describe the largest eigenvalue of these representations in a very nice way, in a complex way. And I just want to say a few words about it. So it turns out that if we take, I don't want to take exactly RKK, I want to take this one. Okay, so here what I did is take the tensor product of this representation with this representation. This is also kind of balanced, and this decomposes as so. First of all, this decomposes. We have our two suspects and the trivial one, so this is already good. And if you look now again, I want to look at the balanced block. So here's I want to show you how the balanced block look like. I want to give a precise example what the balanced block look like when I take in this representation, when I take the hyper edge 1, 2, when n equals 4. And the point is that I want to see if your goal is to recognize, to understand what the process is. What is. So it turns out that in this representation, the coordinates look like that. So you have 1, 1, 1, 2. You have all the multisets of size 2 inside with the elements 1 to 4. So here I have only 1/3. I have 1/2. I have 1. Okay, so basically this is what we saw. It's not exactly how we saw it, but so imagine that I did a lot of work for you. I narrowed down, I looked at, I realized what the central block is, like in the previous example. And now we only look at this the balance block. We look only at this balance block. I tell you that these are good names for the coordinates. And this is what the matrix look like when I look at the edge 1, 2. Okay, so anyone sees that? Anyone sees what these numbers correspond to?
How much intersection do you have with E?
Yeah, but that's not what you want.
Yeah, so I don't understand what's the question.
Okay, yeah, it's fair. I mean, okay, it's not a very clear question. The point is that if you look at the balance block, I'm saying that it describes precisely the following combinatorial process. So we had this process. Well, remember last time we had a hypergraph. We had, for example, one particle, and whenever we chose a hyper edge, what we did was to move this particle to one of the elements of the hyper edge uniformly at random. I'm saying this describes something similar. And it's
3 disjoint sets. So you have two elements, and they just.
So you have basically what you have here is 2 particles. You have the same hypergraph. You have 2 particles. They are identical, and they may sit on the same vertex. You see here I have the 2 particles on the first vertex. Here I have one particle at 1, 1, and 2, and here both of them are 2. So imagine I have this. This is a 1, 2, 3. Sorry, 1, 2, 3, and 4. And I have 2 particles. So let's say one sits here and one sits here. And I have hyper edges, which I didn't draw.
Yeah, so they will travel only between 1 and 2, and sometimes they will both be at 1, sometimes both be at 2.
Yeah, so what I do is whenever if I chose the edge 1, 2, what I do is I look at all the I just take these 2 particles that are supported on my edge, and I take a uniform distribution on all other possible. I can move them around as long as they stay in my edge, and I give all possibilities the same probability. So here I have 3. There can either be all here, both here. They can be 1 and 1, or they can be both in 1. And if my particle is 1 here and 1 here, so I don't touch this particle. This is what happens in this block. I can either move, so I just take this particle and it can either stay or go here with probability 50 and 50. And if both particles are here, this block, I do nothing. So it turns out, again, I have no intuition for that, but this is what the computations show, that I will call this process. So everyone understood the process? Yeah. Questions? So, okay, I don't know about time. I want to say that just, let's say that so we call it MSK. This is the same process. The weighted hyperdomes.
What's MS for?
So this is a multiset. Oh, multisets, because I mean, this is a process on multisets. I have multisets of size K inside which were taken from n elements, n possible elements. Hypergraph W naught with K identical variables. And as far as I know, even though I told you last time that there were other processes that are close, similar to what the original Aldous conjecture with one particle or n different. I mean, we didn't see anyone who actually studied this process, and it turned out that it showed up naturally when you look at Qn, and basically the theorem we have, which generalizes this, is that we'll say like that, the lambda max of K minus K is the same as spectrum of MSK minus the spectrum of MS K minus 1. So you see, I told you that, I mean, here, for example, the largest eigenvalue. So I told you that actually the largest eigenvalue, the set which comes from the balance block of this representation, is the same as this process MS2, the process on two particles. But if I want to know exactly what I get for this one, I need to take out of the spectrum all the eigenvalues I get from one particle. And this shows that the conjecture we started with, is saying, in other words, that is equivalent to saying that the spectral gap of W in UN is the same as the spectral gap of MS2 W. So we get the spectral gap of the analog of the Cayley graph in the unitary group is the same as the spectral gap of this process with two particles. So this is equivalent to the conjecture.
It's equivalent to the conjecture, if the conjecture is true.
Yeah, because the conjecture says that
Right.
the largest eigenvalue comes from one of these, and this theorem says that the largest eigenvalue of one of these is precisely the first non-trivial eigenvalue of this process. Because this process, again, it contains a trivial, so it has a trivial eigenvalue. But then, which by the way, comes just from the uniform distribution on all the multisets, on all the possible positions of the particles. But the second largest comes from one of those. And by the way, I think this is really nice because it gives perhaps it makes this more natural. Why there are two different ones? There's actually, I mean, why there are two representations? Why these two? There's actually a very simple process that captures exactly the largest eigenvalue of these two. So I think it anyway.
When you go to higher K,
Yeah. You get new eigenvalues.
don't you get more representations? It's
We get, yeah, exactly. We get these representations. All of these, we like K000 minus K. You got all of these. So
yeah, they don't decompose. So I mean, you get to this two representations just by arbitrarily telling us about some particular other representation, which is a tensor product of these two
Yeah,
guys on the left.
yes, but I can do it for, this generalized to any k. If I take, if like three k and k, I have here k plus one. It's composed into all the,
Yeah, but you don't want to see the longer one in the
Right.
conjecture.
in the conjecture, yeah, so the conjecture is that in this kind of, in this process with k identical particles, the dominant case is when I have two particles. It's, I guess, larger eigenvalue, the one I get in 3, 4, 5, and so on. And it contains, this contains the one, so, yeah, or in other words, I mean, the process with two particles is contained in process with three particles. You can show how to, but you don't, all the new eigenvalues you get there are not as, at least as large as this one, largest one. You don't get larger eigenvalues. Okay. Any other questions about that?
So can you say that your original conjecture is equivalent to some question just about all these processes or no?
No, because I still have the spectrum graph of UN. No, so no. I mean, it implies there is a weaker conjecture which deals only with the processes, which is that the two particles dominates over each other number of particles. But this is weaker. This just says, so this is equivalent, after what we know, to that these representations. So the conjecture about only the processes, that 2 it controls 3, 4, and so on, means that these two control these and so on, all these representations. It doesn't say anything about the other balanced representations.
So other balanced representations, there's a n to the k by n to the k matrix. You said that you do have some decomposition, block decomposition of those.
Yeah,
But then you still need to kind of analyze all the other representations.
yeah, and we still not, yeah, so we'll see. Yeah, it's a mess. Basically, it's a mess. I mean, I present to you only the things we understand well.
But you can't think of like, so let's suppose R22 is the next one, or? So that's.
So R22 is already, this one's containing R22, but yeah, even R22, it contains other representation. It contains,
That's other.
yeah, it contains, like, for example, this one. This one is balanced, it's containing R22, and yeah. Okay, so now I want to move to something much easier, and you can, it's not going to depend on what we said so far. And to talk about n-1 bubbles, and I will start with Sn. So So now I want to focus on the case where the hypergraph is only supported on n-1 subsets of size n-1. And I want to prove to you, I mean, given some basic facts in representation theory, that Caputo's conjecture is true here, and this is easy. So the conjecture about the symmetric group is easy. And to explain why our conjecture is easier, and therefore, and why we are able to prove it. So I'm not going to give all the details, but for Sn, I want to give all the details. And we need two facts. One of them is what Avi said before. And it's what it said, that if you take an average over the entire group of some irreducible representation, you get 0, unless its representation is trivial. So let G be finite or complex group. and rho and irep. Then the expected value of, I go over all the elements of G, and here I look at a uniform measure or power measure for more generally for G. And this is, so if rho is trivial. Of course, I mean, rho is trivial, each one of them is just a 1 by 1 matrix with 1. And so the average is, of course, 1, right? I mean, you can expect anything else. And otherwise, I just get a 0 matrix for any. Okay, so this is just a fact. It basically follows from shows lemma, those who know it slightly more. And only a corollary from that is this Aldous phenomenon is trivial when all the weight is on the full set. Okay, because when all the weight is on the full set, what do we get? We get eigenvalue of 1 in the trivial representation, and in every other representation we just get zeros. So all the other eigenvalues are 0. So everything is any irreducible representation dominates all the others, because all my inequalities were weak inequalities. So you can just say that now. There was nothing interesting there. Okay.
Oh, around the walk here is the graph.
Yes, yeah, it's like the complete uniform graph, right?
No eigenvalues.
Yes. Yeah, and except for the trivial, all the rest are the same. Yeah, but by the way, this is the complete graph with loops, with self loops.
Yeah.
So it's
Fragment.
yeah. Okay, now fact 2. Branching rule. Okay, what is the branching rule? So first of all, in Sn, so first of all, it's symmetrical on n-1 elements. I can think of it as a subgroup of the symmetrical on n elements. In a natural way, for example, I can take the stabilizer of n, of the element n. So all the permutations, all the permutations stabilize the point n. It's just Sn-1, and I think of it as a subgroup of the symmetrical. Now, if rho is an irrep of symmetrical on n elements, then I can restrict it to the symmetrical point n-1 elements. And this is now a representation, but it's usually not irreducible, right? I get a representation. Remember, this is just a homomorphism from this group to a matrix group, and I just so I still, if I restrict it to a subgroup, I still get a representation, but it's no longer necessarily irreducible. And the branching rule tells you how this decomposes. And in Sn, it turns out that if I take the rho and I restrict it to n-1, then as a representation of S-1, it is a sum of all the representations that are obtained from rho by deleting 1 square. So what does it mean? So remember, representation of the symmetrical are Young diagrams. So for example, if I take this one, this is S7, the symmetrical group S7, if I restrict it to subgroup of permutations that fix the number 7, it's going to be a sum of all the Young representations corresponding to Young diagrams where I omit one square, but I still need to get a Young diagram. So which square can I get? I can remove this one, and this one. I can always remove corners. I can't remove anything which is not a corner. So what I get is this. What's this? Plus this. Okay. So I claim that from this, you can prove Caputo, the Caputo conjecture in Sn for the symmetric group when the sets are of size n-1. And why is that? So Caputo is so the proof is as follows. So if an irref of so when do I get something that is non-trivial when I restrict to Sn-1, the symmetric group on n-1? So again, I mean, so the expected value of this matrix after I change of basis, I change the basis, I get the expected value of this, and then the expected value of this, and the expected value of this. But like we said before, this expected value is just 0 unless I get a trivial representation. So any irrep, if it does not branch to the trivial representation, which is this Young diagram, then the expected value of all the this is just a matrix of zeros. Okay, so again, I assume now that my hypergraph is only supported on sets of size n-1. And I take this random uniform, I take a random permutation according to this distribution on my sets. And because in each subset individually, I can use this branching. And in each of these blocks, if none of them is a trivial, I get 0 in everything. So just everything is 0. Okay, so what do I have left? Which irreps of Sn branch to the trivial? So I need to take this one and add a square, right? I do the reverse. So the only irreps of the symmetric that do branch to the trivial are this one and this one. Right? This is the trivial, we don't care about it. And so the only one that gives us any eigenvalue which is non-zero is this one. Okay, so we're not quite done. Perhaps all the eigenvalues here are negative, but you can show it they're not negative. I mean, the trace is positive, so.
Can you repeat from the start how we got to be interested in the fixing? I mean, one hyperedge is everything but one element, so I understand that's like symmetric on n-1.
Yes.
Why is that somehow?
Because the average of a symmetric group on n-1 vanishes on all representations, but the trivial one of n-1.
Right,
So
But then
what
if
could, but he's interested in symmetric in the representation of Sn. So what could you obtain this trivial on n minus one by the branching rule? It can only come from one of these two.
Okay, so what I'm thinking about is, we're thinking of this process where we have different hyperedges of psi n minus one.
Yes,
So
okay.
how does that like combine?
Right, that's a good question, because I mean, this decomposition on each one of them individually, we will have this decomposition, but you're right, it's not going to be the same, it's going to be different change of basis. This decomposition will be different. So if you just think about it as different subspaces of this, let's say this is 100 dimensional, you have different decompositions with different bases to these three representations for each subset of size n minus one. They don't agree with each other. This is important. But still, in the simple case where, for example, in this if this was the representation,
Meaning if there was only one hyperedge, for example, or?
I'm saying for every hyperedge, doesn't matter what the composition is. I get such a decomposition, but because of the first fact, each one of them is just zeros. So even though I get different decompositions, I get for every n minus one set, I just get the full matrix of this representation is zeros. So even if I sum them up, it's still zeros, and there's nothing interesting. So right. So and the only case, I mean, if I want to apply this rule and get afterward or the trivial representation, which is the only case by this fact, where I get something interesting, then I need to add one block, one square to this one, and I can only add it here and get this, or here and get this to get a valid diagonal.
Obviously, you and others try to do it for n minus two,
Yes,
and it doesn't work.
and it doesn't. Yeah, we don't know. We don't know.
We don't know
We
what
tried
to
and
do.
we don't know what to do. Yeah. Okay. And now, yeah, I guess I'll tell you about why in UN it's not that simple, but.
Sorry, we're done here. What did you say about the next?
Right, so I told you, what I told you is that basically what follows from this, what I wrote is that in every representation which is not one of these, the eigenvalues are just zeros.
Right.
In particular, the maximal one is zero. This one is the trivial, so I know what the eigenvalue is, and anyway, I don't compare to it. I just want to show, so I just want to show that the largest eigenvalue here is non-negative. Because it needs to beat all the zeros. And this is easy because, for example, the trace, you can show the trace here is positive.
Okay.
So you do get the actual, positive eigenvalue. Okay, so now I want to do all of this for a unitary, for the unitary case.
Okay, but the proof of the CLR doesn't proceed in this route, like for
No,
other subgroups or stabilizer and something.
I can tell you over first. I mean, I need like 5 minutes to show the sketch of the proof, but
Okay.
but I want, but I want to say the MS1, and then if you want, you can ask me about it later, and then I can press in the questions. So why n-1 subsets are easier in the unit? Okay, so we try to do the same. What is the branch? We want the branching rule. So the branching rule for it turns out that, so here again, I can take what is the branching rule. I take the subgroup UN minus one inside here. Right? So like before I took SN minus one, so here I take basically this subgroup, where this is one. This is UN minus one inside U. And the question is, I want to take an irreducible representation here and restrict it to this subgroup and ask how does it decompose. And it turns out this is a very beautiful answer with these names, of the representations. So I'll say it like that. So if you take rho mu1 after mu(n), okay, so this is the vector. If I restrict it to un minus 1, turns out that the composition is given by all. So now I need vectors of length n minus 1. I want a representation of un minus 1. And it turns out that these vectors are all the weights that interlace this one. So it's a sum over, let's say, alpha 1 up to alpha n minus 1. Such that u1 is at least alpha 1, which is at least 2, which is at least alpha 2, alpha n minus 1, un. This is
Is it to prove? This is the branching works or not?
Yeah, I don't remember how to prove it actually. So, but it doesn't mean it's not easy. I don't know. But someone else knows. I don't remember.
That's another thing, like, where is it? What's the reference, for example?
Sorry. Book of Bump Bump. What's his name? He has a book on Lie groups. So you can find it there. But I mean, Bump. What's the first name?
I forgot, but
Okay, Bump. Yeah.
thank you.
It surely appears there. Okay, so
We can try to ask ChatGPT.
Yeah. okay, so I mean now okay we have the same thing. Now we have only n minus 1 subsets, and we know that unless we branch the trivial, we're done. All the eigenvalues are 0. So now which are now the problematic ones? Which irreducible representations do branch to the which vector of size n of integers of non-decreasing integers, they branch, they interlace with zeros. Right?
Like, you need just not to have two consecutive positive
Right.
or two consecutive negative numbers.
Basically, no, so you have it. Here, these are all zeros.
Yeah, that's good.
Okay, yeah.
That's
So
exactly.
something here,
You
something
cannot have
here.
consecutive.
I mean, this is negative, this is non,
Positive and not.
yeah, this is non-negative, this is non-positive, and zeros in between. Okay, this is still an infinite family, but yeah, I'll just say it without writing. So first of all, if these are not the same, we already got rid of them. We already treated them. So we are left only with these ones. Now we already know by the other theorem that these are exactly this multiset process. So it's enough for the M-1, it's enough to deal with the multiset process. And in fact, we get something more from the branching. Whenever we do a branching, I mean, by the way, this multiset process on k elements is of order n to the k. This is a large space. But from the branching, we see that in every n subset of size n-1, when we do we actually get more than it. We get that there's only one vector of the trivial representation, right? The trivial representation appears only once. So there's one vector where something interesting happens and all the rest is 0. So if you go over all the subsets, we have overall n subsets of size n-1, we get a subspace of at most, the dimension of the interesting subspace is at most n.
Oh, I'm sorry. Why is this k to the power minus k the only option? I mean. you have
Because,
to replace it.
Because if we have
No,
like
if you
3 zeros
L.
minus 2, this is not balanced and we already deal
That's
with it.
fine,
Got
but
with it.
inside this k and minus k, I can have 3 and minus 3, 4 and minus 4, all these.
Right. Yeah, but yeah, so I'm saying you have k particles in general, not 2 particles. This corresponds, so what I said before, the largest eigenvalue of this, you can find it inside the process of k
MSK.
particles, MSK, yeah. Yeah. And now I'm saying that even more than that, if you think about what the branching tells you is that you actually, inside this process, the MSK is of dimension n to the k, roughly, But in fact, because you have only, you really just look at the trivial representation inside this decomposition, every n-1 set gives you one vector, which it moves, and anything else doesn't move. So you get, you look at the sum of all of them, you get a dimension, a subspace of dimension at most n.
Those are the dangerous ones.
The dangerous one. So we, I mean, this reduces the problem for n-1 sets to dealing with a subspace of dimension at most n, in fact, exactly n, for every k.
And you
And
know which one is will be given the mu's. You know which subset is. N-1 subset.
given which, no, I didn't get size.
So you say only one of the subsets of size n-1 will appear, will give you the trivial.
No, I'm saying that each subset gives you a subspace of dimension 1 where something happened, where because it's the composition, only the trivial part, the trivial representation, is the one where something happens. So every n-1 set will give you only one subspace of dimension 1 where something happens. And the sum of these n-dimensional is an n-dimensional space where all the interesting part happens. And yeah, so now we still need to work, but
And there are disjoints, I mean, these subspaces.
they span
Span everything, but
they span everything. No, there is analysis we need to make with the.
they are orthogonal to each other.
No.
They are not.
I don't think they're orthogonal. No. They're not orthogonal. I'm pretty sure that if I remember correctly, they're not orthogonal, but they are independent. You need to. Yeah, you need to work out. No, it's not immediate. You need to. Yeah. Okay. So yeah, I'm out of time. So we did 5 out of 7. I think it's pretty good.
What was in 6 and 7?
So 6 was to get from to give a sketch of why it's true for the uniform case. So when all the weights are the weight depends only on the size of the average. And 7, and I meant to skip 6 anyway. And 7 was a sketch of the original Aldous. CLR, yeah.
And we ask,
Okay, fantastic. So maybe if you have time sometime in the rest of the week, maybe we can schedule a
Yeah, sure.
follow-up and I'll send an email whoever wants to.
Yeah, it should be like at most 10 minutes. If depends the proof, yeah. The sketch. Okay.
All right, okay, sounds great. Okay, well, thank you, first of all. Are there any questions? Okay, fantastic. All right, thanks so much.
Thanks.